Hi, hello everyone. This is your educator, your tutor, your friend Sanjay Vishwakarma. I welcome you all to yet another session of We Learning. We Learning is a platform which focuses on providing right to quality education for all. Do watch this session. If you like it, do press the like button and share it with your other friends who are preparing for their boards and competition as well. Alright, subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Okay, you can also visit our website www.we-learning.in. You will get all the lecture notes of all the live classes which we are providing here. All right. Okay, now without any delay, let's get started with today's session. We were doing electrostatic potential and capacitance, and this is lecture number 8. In this lecture, we are going to talk about electrostatics of conductors and dielectric and polarization. Now, both these topics are not very important if you are thinking in terms of marks. Maybe a 1 mark question will be asked in board exam, not more than that. But in terms of concept, if you think this is important, okay. All right. So now let's start with electrostatics of conductors. We have already seen conductors, electric field, potential, inside, outside, in a conducting sphere, non-conducting sphere. We've already seen, right? It is just a summary kind of a thing for that. Okay. Understand. Now, first, the interior of a conductor can have no excess charge in the static situation. Why we are discussing electrostatics of conductors? Because after this, we'll be starting with capacitors. Okay. Capacitors are nothing but the capacitor plates are nothing but conducting plates. For that, you should know how conductors behave. Okay. Conductor is something which holds a lot of charge. It is an ocean of electrons, right? It holds a lot of charge. Capacitor plates also hold a lot of charge. So once you know this, then it will be easier for you to understand that. Okay. Now, the interior of a conductor can have no excess charge in static situation. What does this mean? Normally, if you see a conductor, okay, it's a 3D. It's not just a plate. It's a conductor. Okay. Now, in this conductor, normally they are neutral. All right. The amount of negative charge and the amount of positive charge is equal. If I give charge to it, that will be an excess charge. Right now, electron is equal to proton, or negative charge is equal to positive charge. If I charge it, that will be an excess charge which I am giving to it. Okay. Now, let's say a lot of positive charge I have given to it. What will happen? That positive charge, if I give a lot of positive charge to it, the positive charge will not stay inside. It will come out on the surface. It will come out on the surface. All right. So interior of a conductor has no excess charge. Inside this conductor, there is no excess charge. All the excess charge will come to the surface. Clear? Very easy to understand. Next, inside a conductor, electrostatic field is 0. Again, very simple. If this is the case, let me make it here. Let's say this is a conductor. All the charge what I have given, all the excess charge is here at the surface. If the excess charge is there at the surface, inside there is no charge, right? Inside it is neutral. Inside there is no charge. So that means electric field inside will also be 0. See, if there is a point charge positive, we know that electric field originates from here. If there is a negative point charge, we know that electric field will terminate here. Now here the positive charge is starting from the surface only, right? If you see, this electric field line will start from here. If I make electric field line, it will be like this. It will start from here. Inside there is no electric field line. It is originating from here. Okay. This way also you can understand. There is one more way to understand. Gauss law, if you go to chapter number 1, right? Now, if I make a Gaussian surface inside this, let's say, if I make a Gaussian surface inside this, now flux through this Gaussian surface, I can write E dot A is equal to Q inside upon epsilon naught. Gauss law, it is a closed surface, right? E into A, or E vector dot A vector, and then this theta will be 0 degrees below, because electric field will be perpendicular to the surface. Electric flux we take perpendicular to the surface. All those things, okay? Gauss law, from here Q inside is equal to 0, so EA will be 0. Area is not 0, that means electric field is 0. Very simple. correct? So now there are a lot of ways to understand why electric field inside this will be 0. Okay, since there is no charge, electric field inside will be 0. In every conductor, this is true. Whatever be the shape of the conductor, this is true. Okay, all right. Next, at the surface of a charged conductor, electrostatic field must be normal to the surface at every point. Again, this also we know. I'll just tell you by example, I'll just prove you why it should be perpendicular. Okay, if this is the electrostatic surface, if this is the conductor, now there is a charge here, positive charge. Now they are telling that electric field lines should be normal to the surface. That means electric field line and surface should be perpendicular to each other. Electric field line and surface should be perpendicular to each other. Now let's say you are asking why, sir, why is it so? Let's say they are not perpendicular. Okay, let me make this at some angle. Okay, let's say this electric field is at some angle theta. Fine, it is at some angle theta. It will be having two components. One will be perpendicular component, one will be horizontal component. Perpendicular component means E sin theta, this will be E cos theta, correct? E sin theta and E cos theta. E cos theta is the component which is along the surface. E sin theta is the component which is perpendicular to the surface. E cos theta is along the surface. This is perpendicular to the surface. Now see, since this is along the surface, there is one more positive charge which is beside this, right? If this electric field will go along the surface, this charge is also on the surface. This electric field will repel this charge. This electric field is due to positive charge only, right? This electric field will repel this charge. Because of this repulsion, this charge will start moving to this side, correct? On the surface only. Now see, if this charge starts moving here, it will repel this charge. This charge will also move a bit here. Once this comes close to this charge, this will repel this. Then this will move here. This will repel this one. This will move here. This will repel this one. This will move here. It will repel this one. This will move here. It will repel this one. Like this, every charge will start moving because of this. Once this comes closer, this will feel repulsion. It will move away. Again, this will feel repulsion. It will move away. Like this, the flow of charge will start. See? Current will be formed on the surface. The flow of charge will start. Flow of charge is only possible when there is a potential difference, right? Flow of charge is only possible when there is a difference in the potential. Then only it moves from higher potential to lower potential, correct? And we know that on the surface of the conductor, the potential is constant at each and every point. We have already seen, right? In case of sphere, if you remember, we have already seen at the surface, the potential is constant. The potential difference between any 2 points on the surface will be 0. If there is no potential difference, this charge cannot flow. This charge cannot flow. That means if charge cannot flow, this E cos theta should be 0. There should be no electric field along the surface. If E cos theta is 0, that means theta is equal to 90 degrees. That means theta is equal to 90 degrees. Clear? So this theta was any arbitrary angle at which this electric field is there. Then we took two components of that. So if this is 90 degrees, E sin theta will be E sin 90, that is E. Electric field is actually in this direction, that is perpendicular to the surface. Clear? Okay, next. I hope you will remember this. Okay, let me just erase it quickly. What you have to remember, if this is a conductor, there is a lot of positive charge, excess charge. The electric field due to this excess charge will be normal to the surface. Will be normal to the surface. Clear? Next, electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. Okay, if there is a conductor, potential inside and potential at surface both are equal. Anyways, we already saw this in case of sphere. That is true. V at surface is equal to V inside. V at surface, it is always constant. Electrostatic potential is constant throughout this volume. Whatever is inside will be same as the one which is on the surface. Okay. Why this is so? See, if the potentials were not same, the flow of charge will start, right? The charge will start flowing from here to inside. But we know that on a conductor, the charge doesn't remain inside. It comes on the surface. It is always on the surface. There is no movement of charge. This is static condition, right? That means the potentials are same. Because if there will be a potential difference, the charge will flow inside. Correct? That's the reason the potential, there is no potential difference. Inside and outside potential is same. Practically, it has been seen that the charge doesn't go inside. The charge movement doesn't take place. Practically, because this is a static condition, Vs is equal to Vin. Fine. Next. Electric field at the surface of a charged conductor is sigma upon epsilon naught. What is n vector here? The direction of electric field is normal to the surface. Okay. Sigma upon epsilon naught. Again, we have already derived this also when we saw a plate, an infinite plate, a conducting plate having a lot of charge, right? There were two plates. Between that, we saw electric field sigma upon epsilon naught. That is the same thing. Electric field at the surface of a charged conductor is sigma upon epsilon. Next, electrostatic shielding. What is electrostatic shielding? Nothing, no rocket science. Electrostatic shielding means if there is a conductor, now this conductor is having charge, right? Excess charge is on the surface. If there is a cavity inside this cavity, the electric field will be zero. We know that if it was a complete conductor without a cavity, electric field will be zero inside. But if there is a cavity also, electric field inside will be zero. Given that there is no charge at the center, there is no charge inside this cavity. We have not given any charge. We have not put any Q inside this. That is not the case, okay? Due to this excess charge which we have given to the conductor which came on the surface, now inside this cavity, electric field will be zero. Inside the cavity, E is equal to 0. Okay, this is cavity. This is cavity. Fine. Okay. So electrostatic shielding means this cavity is shielded. Okay. Electric field will always be 0. This is what shielding is. Next. So these were the 6 properties of conductors which will always be true for any conductor of any shape and any size. Okay. Now let's see dielectrics. Conductor is also material, a kind of material which is conducting. Dielectric is also a kind of material which is not conducting. It is neither a conductor nor you can say an insulator also, because this is a material which will not allow free electrons to flow inside them, because there are no free electrons. There is no free charge which will flow inside this material. There is no flow of current in the material, but a formation of electric field will be there. Dielectric is a kind of material in which the flow of current will not be there. When this dielectric will be placed in an external electric field, there will be the flow of current cannot be possible in this dielectric, but a formation of electric field is possible. Okay. Dielectrics are insulating material which transmit electric effects without actually conducting electricity. Electric effects means they will allow electric field to be formed inside them, but there will be no flow of charge in that. Okay. So now there are two kind of dielectric material. Dielectrics. There are two types. Okay. One is non-polar. One is polar. Okay. What is non-polar and polar? If you see at molecular level, okay, if you see all as a complete material, if you see, you will not understand. But if you see at a molecular level, non-polar means the dipole moment is equal to zero. Clear? Polar means dipole moment is not equal to zero. Fine. Here dipole moment will be zero of that particular molecule. Here the dipole moment will not be zero. For example, let's take H2. Let's take H2. Now H2, one hydrogen atom will be like this, one hydrogen atom will be like this. Correct? Both are of same size. There is no transfer of electron. Right? It's not like it is not giving any electron here. There will no charge will develop at both the atoms, right? So because of which the dipole moment is zero. Dipole moment only happens when there is a positive and negative charge at some separation. Here no charge is being developed. The electron transfer is not happening. Correct? Or you can say the center of positive and negative charge is coinciding to each other, because of which this is a non-polar thing. I'll explain you what is coinciding. I'll explain you later. Okay. If you see carbon dioxide, one carbon will be like this, oxygen will be here, one oxygen will be here. Okay. Here also this is non-polar, dipole moment will be zero. Here example HCl. HCl, if you see, H plus will be there and Cl minus will be there. Correct? H plus will be there and Cl minus will be there. Since there is a charge, since there is a transfer of charge, okay, because of which this will be, the dipole moment will not be zero. There will be some dipole moment here. Okay. Other example can be water. H2O. See, one oxygen will be here. Hydrogen atoms will be sticked like this. Hydrogen, this will be oxygen. Correct? This oxygen is having minus 2E. This hydrogen is having plus E. This is also having plus E. Because of which, if you see, these are at some separation. If I just try to make a virtual center of it, the center will come here. That is plus 2E. See, minus 2 is here, plus 2 is here. There is a difference, because of which a dipole moment will happen. There will be a dipole moment. Okay. Non-polar and polar. Again, if you want to write, you can write non-polar dielectrics. The molecules in which the center of positive charge coincide with the center of negative charges are called non-polar molecules. Such molecules are symmetric in shape. Okay. Example: O2, CO2, methane, etc. Next, polar dielectrics. The molecules in which the center of positive charge does not coincide with the center of negative charge because of the asymmetric shape of the molecules are called polar molecules. Okay. Example: HCl, H2O, NH3, etc. Note it down if you want. All theory, it is all theory. Next, now let's understand polarization. Dielectrics, I hope you got to know. Dielectric is a material which is not a conducting material. We cannot say it as complete insulator also. It is a non-conducting material. You can understand that way. Okay. Examples are glass, mica, rubber, all these. Alright. So now these are the material which will not allow electric current to flow through it, but they will allow electric field to be formed inside them. Okay, there are two kind of dielectric material, one non-polar and one polar. Molecular level, if you see, if you go at a very molecular level, if you see, you can understand what are non-polar dielectric materials and what are polar dielectric materials. Now let's see polarization. What is polarization? Polarization of non-polar dielectrics, let's see first. Now suppose this is a dielectric material. Okay, if I see it at molecular level, there will be molecules inside. At an atomic level, if you see here. Now in these, Negative charge, positive charge, negative charge, positive charge, negative charge, positive charge, negative, positive, negative, positive. Like this it will be. Here, the dipole moment of one molecule is zero. Obviously, because of which the net dipole moment of the entire material will also be zero, right? So P net, here there is no electric field, there is no external electric field. This material is just kept like this. Electric field is zero, and P net will also be zero. P net will also be zero. Why? Because of one molecule only, the dipole moment is zero, because of which for this entire material, the dipole moment will be zero. Correct? Now see, coinciding the center of negative charge and positive charge means what? Normally, in an atom, if you see, this is positive charge is at the center. Okay? And electron is here. Correct? If you see the orbit of this electron, the center will be here. And if you see the positive charge, which is already at the nucleus, the center will be here only. Since the center of the electron and the proton is coinciding, because of which the dipole moment of this will be zero. Okay? Clear? What does coinciding of center means? All right. Now here, but what happens when we put it in an electric field? There is an electric field. I'll put this in the electric field. Okay. Now what will happen? See here, again, in an atomic level only, if you see, this is a positive charge, this is an electron. Okay. Once the electric field will come, the negative charge will move opposite to the electric field and the positive charge will move towards the electric field. That means what will happen? What will happen to this? This positive charge will move this side and this electron will try to run this side. No doubt it will be moving like this, but this electron will move this side and positive charge will move this side. Now the shape of the atom is not circular. The shape of the orbit of this electron is not circular. Correct? Because of which the center of this negative charge will not be here. For this positive charge, the center will be here. For this negative charge, the center will be somewhere here. Right? Now see, there is a difference. Positive charge, negative charge, if they are kept at a separation D, dipole moment is Q into D. That's what we have learned in physics, correct? So dipole moment will be there when the charges are kept at some separation. Here, just because of this electric field, this charge will come this side, this positive will shift this side, the nucleus will be this side, this orbit will be shifted a bit like this, right? It will not be a circular one. The center of this will be this. Now there is a separation. Here it was coinciding. Here they are at separation. So now the net dipole moment will not be zero. Clear? Now the net dipole moment will not be zero. Why? It is something like this. It will become something like this. Here if you see, electric field is not zero and P net is also not equal to zero. When electric field was zero, in dielectric material, P net will be zero. When electric field is not zero, P net will not be zero. Okay? Dipole moment will not be zero. This is what polarization is. This is what polarization is. Here if you see, this particular side of the plate, of the material, this thing, if you see this surface of this material and if you see this surface of this material, what can you see? This surface of the material is negatively charged and this surface of the material is positively charged. Correct? Correct? I'll explain this properly. First, let us see what happens when electric field is run over or when a polar dielectric is kept on a kept in a electric field. See here, polar dielectric, if I talk about, in this what will happen, P net, P of one molecule is only not zero, right? For one atom also, if you see, it is not zero. P net will not be zero, correct? Right. See here, P will be like this, P will be like this, P vector, okay, from negative to positive. P vector will be like this, P vector will be like this, P vector will be like this. If you see P vector, the direction, if you see for this particular molecule, P is not zero. P is not zero, but P net will be zero. Why? These molecules, they will arrange themselves in such a way, that the net dipole moment comes as zero. All right. Fine. P net of this entire material is zero. That is why it is dielectric. Okay. P net of this entire material is zero. Now see, once this is kept in an electric field, what will happen? Okay, I already have this. Again, they will align themselves according to the electric field. In whatever alignment they were, once the electric field is on, they will align. The negative charge will move away from the electric field and positive charge will move towards the electric field. Okay, the final arrangement will be like this. Clear? This is the dipole moment now. So now the net dipole moment is not zero. When electric field is not zero, P net is also not zero. Clear? In whatever alignment they were before, once the electric field is on, positive charge will move towards the electric field, negative charge will move away from the electric field. They will align themselves like this. All right. All right, here E is zero. Fine. P net is also zero. I'll write here only. Now see the thing here, when it was non-polar, E 0, P net 0, E not 0, P net not 0. In polar also the same thing, E 0, P net 0, E not 0, P net non-zero. The only difference is if you go to molecular level and see, then you will understand that here these dipoles are not arranged properly, and here the dipole moment will be there, molecular level also, but in non-polar the dipole moment will not be there. Okay, but overall if you see, net dipole moment will be zero if there is no electric field. All right, now let's understand polarization properly. So finally what we got to know is, it will be something like this. Whether it is a non-polar dielectric or a polar dielectric, once the electric field is on, it behaves same. Now see, if you see this side, as I already told, complete negative charge is there. If you see this side, complete positive charge is there. Correct? This is negative, this is positive. Now there was an electric field. Let's say this original electric field is E naught, the initial electric field. Okay, when there was no dielectric in the when there was no dielectric present, okay, it was E naught. Once we enter a dielectric in this field, this polarization will happen. Due to this polarization, understand, this side will be positively charged, this side will be negatively charged. Now if there are two sheets, this is completely negative charge, this is completely positive charge, we know what will happen: an electric field from positive to negative, correct? The same thing will happen here. What will happen? An electric field from here to here, that is E due to polarization will come. E due to polarization will flow from here to here, electric field. All right. Now E naught was this side, EP is this side. So what will be the net electric field in this material? Or here if I ask, what will be the net electric field? It is a vector, right? We will add them, vector sum, E naught minus EP. E net inside this, or let's say E net is E inside this is E naught minus EP. E inside this material will be E naught minus EP. Okay, because this electric field was there, which was in this direction. Electric field due to polarization or induced electric field, whatever you say, is in this direction. Net electric field inside this will be E naught minus EP. Okay, clear? So finally what will happen? The electric field will be reduced. So whenever there is an electric field, if we want to reduce the electric field, we can put any dielectric material in that electric field and the net electric field will be reduced. Okay, this we'll see in the capacitance. When we'll see dielectric effect of capacitance, then we'll see this. All right. Next, electric susceptibility. What is electric susceptibility? See here, this was E naught. We finally got to know that an induced electric field will be like this, or polarized electric field due to polarization will be like this. So the net electric field will be in this direction, that is E naught minus EP. Okay. Acha, why net electric field will be in this direction? If you do the vector sum, this is in this direction, this is in opposite direction. This will always be greater than this. E naught will always be greater than E polarized. Why? Because this electric field is produced because of this electric field. Correct? This electric field was produced because of this. This will always be greater than this. Clear? Now, what is electric susceptibility? Understand, the more strong is this electric field, the more will be the polarization. Correct? Polarization is happening. If this electric field is more strong, let's say this is atom, this is positive charge. If electric field will be very strong, this negative charge will move with more speed. This side will move more, right? If the electric field is not strong, it will not move more. If it is very strong, it will move more. The distance will be more. The dipole moment will be more. The polarization will be more. Correct? That means polarization is directly proportional to the electric field. Are yes or no? Polarization is directly proportional to the electric field. Okay? Polarization is directly proportional to the electric field. Now polarization is equal to, if I remove this, it will be epsilon naught xe into, this is not x, this is chi. We write like x. This is chi. Okay. Epsilon naught chi into E. This is polarization. Remember this. This is polarization. What is this? What is this? This is electric susceptibility. This is electric susceptibility. Okay. This is polarization is directly proportional to electric field. P is equal to epsilon naught chi into E, and this chi is electric susceptibility. Okay. Now, this chi is basically, the formula of electric susceptibility will be P upon epsilon naught E. It is the ratio of polarization to electric field. It is the ratio of polarization to electric field. Chi is basically an intrinsic property of any dielectric material. The more will be this chi, the more will be the polarization. The more will be this electric susceptibility, the more will be the polarization. Right? So susceptibility is the property of dielectric material. Okay. Now somewhere you would have seen this formula as P is equal to chi into E, correct? Somewhere you would have seen like this. Maybe you would have scratched your head, why this formula is different? It is not different. This is in CGS system and this is in KMS system. Okay. Since we are studying KMS system, kilometer second, right? Since we are studying KMS system, for us, in your books, you will find this formula. In some books, this formula will be there. Okay. From this formula, it comes as chi or electric susceptibility is equal to polarization upon electric field. It is the ratio of polarization to electric field. Okay. Net electric field. So both are correct. Only the system is different. Fine. Because of this difference in the system, the chi E in KMS system is equal to 4 pi times of xe or chi E in CGS system. It is the 4 pi times. This electric susceptibility in KMS system is 4 pi times the electric susceptibility in CGS system. Okay. No need for this. Just for your information, I am telling you. In your CBSE books, this formula is given because we are following KMS system. Okay. P is equal to epsilon naught chi E into E, and electric susceptibility is polarization to electric field ratio. Fine. Okay. Now let's see the relation between dielectric constant and electric susceptibility. What is dielectric constant? This is termed as K. Okay. What is this? What is this? This is basically relative permittivity. You have studied in first chapter, epsilon R. Relative permittivity is equal to epsilon of medium upon epsilon naught, correct? This is nothing but K only. It is nothing but dielectric constant. This was the relative permittivity of the medium, right? This was permittivity of medium, this was permittivity of free space. This was the relative permittivity, that means permittivity of medium, the ratio of permittivity of medium to the permittivity of free space. That is only dielectric constant. Okay. Okay. Now see. Okay, from here K is equal to epsilon R, that is epsilon M upon epsilon naught, and that is also equal to, if you remember, that is also equal to E, electric field in free space, or E naught upon E, correct? Remember this. Now this derivation, there are two ways to derive this relation between electric constant and electric susceptibility. One I'll get from this. This is epsilon, this is E. Okay. See here how it is done. Now electric displacement is equal to epsilon naught E plus polarization. Okay. Electric displacement is equal to epsilon naught E plus polarization. Epsilon naught E plus polarization is epsilon naught into electric susceptibility into E, and this D is equal to epsilon E. Electric displacement is equal to epsilon E. Okay, that is equal to, from here if you see, this E will be cancelled, this E will be cancelled, this E will be cancelled. What we have got finally is epsilon is equal to epsilon naught. If I take epsilon naught common, this will be 1 plus electric susceptibility. This epsilon naught, if I take to the other side and divide, epsilon upon epsilon naught is equal to 1 plus this, and this we know that this is K, dielectric constant, 1 plus. Remember this. One mark question from this can come in boards. K is equal to 1 plus electric susceptibility. Okay. Other way to get it, if you don't remember this formula, electric displacement is equal to epsilon naught E plus polarization, then one thing you will always remember. Okay. What is that thing? E net final electric field is equal to E naught minus E due to polarization, correct? Just now we saw final electric field, net electric field will be E naught minus E due to polarization. Now this is E naught minus, what is E due to polarization? Sigma upon epsilon naught. We have seen in conductors on the surface the electric field will be sigma upon epsilon naught. So this will be sigma due to polarization upon epsilon naught. Now this sigma due to polarization I can write here P. This is polarization only. This sigma is charge per unit area, right? Charge density, surface charge density. Polarization is also surface charge density. These two are same things. I'll show you how. See here. See here. Okay, one more thing I wanted to tell you here only. Polarization is equal to P net. This is dipole moment. This is capital P is polarization. Small p net is dipole moment per unit volume. I am not writing V because some people confuse it with voltage, potential. Polarization is equal to net dipole moment of this material divided by the volume. This is what polarization is. Okay. Now see, net dipole moment. I told you this sheet will have a negative charge. I mean this side a negative charge will come. This side a positive charge will come. Correct? If I make it 3D, see here. This is a dielectric material or dielectric box kind of thing, fine. I mean a cuboid kind of thing. So now this surface will be negatively charged and this surface is the one which is positively charged, correct? Because the electric field is passing from these surfaces only. The electric field is passing from these surfaces only. So this will be negatively charged, this surface will be positively charged. Correct? Because of which, suppose if this is minus Q, this is plus Q, let's say, there is a separation between this D. What will be the dipole moment? This is like minus Q, this is like plus Q. This is a separation D. Dipole moment is equal to Q into D, correct? So due to the polarization, the net dipole moment, this formula first of all you have to remember, okay? This formula you have to remember. Polarization is equal to net dipole moment per unit volume. This is also important, okay? Now, net dipole moment, P net, just for your understanding this is equal to Q into D. And volume is polarization. P net is Q into D, volume is, if this surface has A, if this surface has area A and this thickness is D, let's say, so area A into D and D will be cancelled, charge per unit area. This is charge per unit area. Charge on these sheets per unit area is polarization, right? So now that sigma I can replace by P. That sigma here I can replace by P. Correct? What is P? What is P? Epsilon naught chi E into E divided by epsilon naught. Correct? From here, see, this and this will be cancelled. Correct? From here, this chi E into E will come to the other side. So E common 1 plus chi is equal to E naught. From here, E naught by E is equal to 1 plus chi. And what is this? K. What is this? K. K is equal to 1 plus chi. Clear? So from here also you can get, from here also you can get. This is the main derivation. This is the main derivation. Okay, that is for your understanding. If you are not remembering this and you forgot the formula you want to get, you can replace that sigma with this P and get the answer. Okay. Now let's see the question. What kind of question will be? Find the susceptibility of a material whose dielectric constant is 2.26. So dielectric constant is given as 2.26. We have to find the susceptibility. 1 plus susceptibility is equal to K. So susceptibility is equal to K minus 1, that is 2.6 minus 1, that is 1.6. Can you see the option 1.6? Yes or no? Okay, this is the answer. Easy. Like this 1 mark question can come. Let's see one more kind of question. The relative dielectric constant. The relative dielectric constant of polystyrene is 2.5. K is given to be 2.5. Okay. What is the polarization produced when 0.5 mm thick sheet of polystyrene is subjected to 220 volt? V is given to be 220 volt. Thickness is given to be 0.5 mm. D is given to be 0.5 mm. Okay. We have to find polarization. Just put this in the formula, you will get the answer. Polarization is equal to epsilon naught into susceptibility into E. Clear? K we know, susceptibility is K minus 1. That is equal to 2.5 minus 1, that is 1.5. Epsilon naught is 8.85 into 10 power minus 12. Put here 8.85 into 10 power minus 12 into 1.5 into E. How much will be E? How much will be E? V by D. Correct? That is 220 divided by 0.5 mm. 0.5 into 10 power minus 3. Solve this. This 3 zeros will go up. This point, if we remove one more zero, will go up 4 zeros. So after 22, 5 zeros, then 5 and 220, 44. And then 4 more zeros. Correct? This will be the electric field. And multiply by 440000. If you solve this from calculator, you will get 5.84 into 10 power minus 6 coulomb per meter. This is polarization. Okay, 5.84 into 10 power minus 6 coulomb per meter. This is the answer. Clear? Done. See, logically understand. It's not like we have just put in the formula. There was a sheet. There was a sheet. It was having some thickness. Correct? Subjected to 220 volt means this side and this side of the sheet is having potential difference. Let's say this is 0, this is 220 volt. Okay. So in this thickness, there will be electric field. Right, the thickness in which the electric field is 0.5 mm. That's why this E is V by D. This potential difference is due to the electric field in this thickness, right? So E is equal to V by D. From there we got the E, and then we have put in the formula. Okay, got it? So I hope you understood today's session. If you liked the session, do press the like button. In the next session, we'll be doing introduction to capacitors, very important. Okay, capacitors, now we are going to start the next, potential is done. Now conductors, electrostatic of conductors and dielectrics were, before the capacitors should start, that should be clear. So now we'll be going to start capacitors in the next session. Okay. If you like today's session, do press the like button, share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Okay, we'll meet up in the next session. Till then, keep learning from We Learning. All the best.